A sequence is defined as a function whose domain is the set of positive integers 1, 2, 3, basically denoted as A1, A2, A3, all the way till AN. So a sequence is defined as a function whose domain is a set of positive integers 1, 2, 3, etc. represented this way. These are the terms of the sequence. A sub n denotes the nth term and the sequence. Let me rephrase that better. And the sequence is denoted as A sub n. Okay, so let me show you real quick what a sequence looks like. So the homework will start this way. Find the first 5 terms of the sequence. So let's get used to the notation. A sub n is equal to n squared over 2 to the n minus 1. So A sub 1 is equal to, literally just plug in the 1 squared over 2 to the 1 minus 1, which is 1 over 1, right? Which is 1. A2 would be 2 squared over 2 to the 2 minus 1, which is 4 over 4 minus 1, which is 4/3. So just keep going this way. A3 will be similar, so it'll be 3 squared over 2 cubed minus 1, which is 9 over 8 minus 1, which is 9/7. A4 will be 4 squared, 2 to the 4th minus 1. So as you can see, it's just a pattern, right? This will be A4, 15. So you see the pattern right here, right? 4, 3, 9, 7, 16, 15. Last one will be 25, 31. So the answer would simply be just listing these numbers. 1 4/3, 9/7, 16 15s, 25th 31s. Okay. So that's the first thing that you need to know is the notation to do sequences, is make sure you know that A sub n is the general formula for the sequence. which is basically a function that's defined as on integers, positive integers. So A1 means plug in 1, A2, etc. Okay. Any questions about the basics? Okay. So example 2 talks about notation for factorials. So they're going to need that during the this chapter. So let's review that a little bit. So simplify the ratio of factorials. Okay. So a factorial basically, before we get to example 2, so let's say you had, let's make it simple, 3 factorial. That's your exclamation point. So 3 exclamation point means 3 factorial, which is telling you to do 3 times 2 times 1. You should have seen this in college algebra. 5 factorial would be 5 times 4 times 3 times 2 times 1, right? Which is what? 6. 5 times 4 is 20. I think it's 120, right? Anyway, n factorial. Well, also one last note. 0 factorial is equal to 1. 1 factorial is equal to 1, just by definition. But just to refresh your memory with numbers, that's what the factorials represent. Okay. So let's see here. Yeah, that's fine. Note before we start this example, n plus 1 factorial means you start with n plus 1, and then you keep subtracting. You see what I'm saying? All the way until you get to 0 factorial. That's what we did here, right? So in general terms, you start with whatever's in there, and you start subtracting by 1. Just like we did here, 5, 4, 3, 2, 1. All right. So the example for this problem will be simplifying this guy. 2 to the n factorial over 2n plus 2 factorial. So you need to expand the factorials, similar to what we did here, until you can cancel the bottom. Notice how the bottom is bigger, right? Is 2 more than the top. So if I expand this a little bit, I should be able to cancel this. So I'm going to leave the top alone. And on the bottom, do 2n plus 2, 2n plus 1, 2n. And then right there, I'm going to stop. You see how I subtracted 1, subtracted 1. I can keep going. Right? I can do 2n minus 1, 2n minus 2, all the way forever. But now that I'm here, I can cross this out. Notice how I no longer have any factorials. I have simplified it into 2n plus 2 times 2n plus 1. So you have to be you'll have to be able to simplify the factorials. Okay. Is there any questions on factorials? Just a brief review. All right. So let's get back to sequences, but first we need to define or write down a definition of a limit for a sequence. Definition of the limit of a sequence let L be a real number the limit of a sequence a sub n is L, written as the limit as n approaches infinity of a sub n equal to L. And the definition continues. So the limit of a sub n is equal to L for each epsilon greater than 0. There exists that's a symbol that we usually use. I believe it's delta. Yeah, we'll use capital M. There exists a capital M greater than 0 such that the absolute value of a sub n minus L is less than epsilon whenever n is greater than m. If the limit exists, then the sequence converges to L, which is what we're going to be doing, is checking is there a limit, and if there is, it converges to that limit. If the limit does not exist, then the sequence diverges. So that's what I'm going to have you do in these problems and in the homework, etc., is check, is there a limit? Okay. So similar to what you did in Cal 1, you're going to apply it to what's it called? Sequences. Okay. And here's some properties of sequences real quick. The room, I think, is 9.2 in the book. Properties of limits of sequences. One moment. Excuse me. Sequences, okay. Let the limit of a sub n equal L as n approaches infinity. And the limit as n approaches infinity as b sub n equal to k. So you have two different limits. So property number 1 is called the scalar multiple. Okay. So basically, if you have the limit as n approaches infinity, If you have a scalar on your sequence, then that can be equal to the scalar times your limit L, where C is any real number. Number 2, sum or difference. If you have the limit as n approaches infinity of the two sequences, a sub n plus or minus b sub n, that will equal to L plus or minus K. So you just add the limits that we already knew existed. Number 3, if you multiply these sequences together, so this is the product, the limit of a sub n times b sub n is equal to, as n approaches infinity, L times K. Number 4, is the quotient. I don't know why my pen's dying on me now. I think there's something on the paper. Yeah, I'll just do it on a different page. I guess all these are trash. Go open another pack. It's hilarious. Jesus Christ. All right. Quotient. The limit of a sub n over b sub n is equal to L over K. Assuming that K is not equal to 0. All right. So we'll start with example 3. Find the limit of the sequence the limit as n approaches infinity of 3n squared over n squared plus 5. So this limit is going to be 3 over 1, right? Using our properties from Cal 1. You guys remember why this is 3 over 1?
L'Hopital's?
Um,
Wait,
well, kinda. Yeah, actually, in this case, L'Hopital would give you 3. That's true.
okay, I just wondering.
Yeah, but also the other idea was if the degrees of the numerator and denominator are the same, you just take the coefficient of the highest uh, of those numbers, so the 3 and the 1.
Oh, yeah.
But since the limit exists, then uh, the sequence converges. So you would say on a test, if I gave you a sequence and asked you if it converges or diverges, you'd say since the limit exists and is finite, then the sequence 3n squared over n squared plus 5 converges to 3. Okay. So they weren't asking that yet, but I'm just going to go ahead and start answering it this way because that's what they're all going to ask for. Okay. Any questions on example 3? All right. Example 4. Determine if the sequence converges or diverges. And in this case, I'll put parentheses here, find the limit. That's what you're going to do, right? That's how you find out if a sequence converges. It's all about the limit. Okay, so part A, the limit as n approaches infinity of n over n plus 1. So we can see that this limit is going to be 1. So converges to 1, right? Part B, take the limit as n approaches infinity of negative 1 to the n of 3n squared over n squared plus 5. So it looks like it might have the same kind of situation, but notice how there's a negative 1 to the n. This is going to create an alternating piece, right? Because when it's odd, it'll be negative. When it is even, it'll be positive. So it'll always keep switching, meaning it doesn't converge to a single value. The limit will not exist because of the alternating piece. Does that make sense?
You repeat that?
So let's think about this with a simple. Let's say we had a negative 1 to the n times 5, right? let's say that's your sequence, a sub n. So a1 would be negative 1 to the 1 times 5, which is negative 5. A2 would be negative 1 squared, right? Times 5, which would be a positive 5.
Oh, I get what you're saying now.
So
Like you'll
this,
keep going. Yeah.
yeah, so this alternating, so since the sequence keeps alternating, it will not converge. Even though it
Mhm.
looks like it's always 5, but no, it's not always 5.
Yeah.
So the limit for this one doesn't exist. Neither does it exist for this. So does not exist. You would say for B, I'm going to write the answer appropriately. Since the limit does not exist, then the sequence diverges. So for 9.1 is all about sequences, which means it's all about what's it called? The limit. Okay. Okay. Let me mention the squeeze theorem really quick. Theorem 9.3, squeeze. So if the limit as b approaches infinity of a sub n is equal to L, which is equal to the limit of b sub n as n approaches infinity. This should be an n actually. Sorry. Oh, there's a bunch of crap on here. Okay. And there exists an integer n such that a sub n is less than c sub n, less than or equal to b sub n, for all n greater than n, then the limit of the one in the middle being squeezed together or squeezed by the others will equal to L as well. Okay. Let me give you an example real quick as to what that means in case that's not clear. So basically, I'll draw it out in a second, but if you know that there's a smaller sequence and a larger sequence, and those both converge to the same thing, and you know for a fact that C sub n is in the middle, then that one will also converge to that same value. Okay. This is a quick explanation. Let's see, we have, so we know that sine of n is between 1 and 1, right? And we know that if I were to divide all these pieces by n, it would still be less than. So if I were to take the limit as n approaches infinity of this three-way thing here, this is supposed to be negative. Sorry about that. We know that this limit will go to 0, right? this will also go to 0. Does that make sense? Which means that the middle, so since sine n over n is being squeezed, right? Then its limit is also 0. That's basically what, I mean, this is very informal, but that's basically what that paragraph was saying earlier that we wrote, that we were talking about the squeeze theorem. Does that make sense? One last definition, and we'll move on to 9.2. Definition of a monotonic sequence. So if the homework asks you, is a sequence monotonic? You just gotta check this definition. So a sequence A sub n is monotonic when its terms are non-decreasing so basically a sub 1 is less than a sub 2, which is less than a sub 3, which is less than a sub n. Okay? Or a sub 1 is greater than a sub 2, which is greater than or equal to a sub 3, which is greater than or equal to all the way till a sub n and beyond. So basically, if it is decreasing or let's see how it praise or increasing, then it is considered to be monotonic. I don't know why the book uses non-decreasing and non-whatever. It's kind of backwards now that I think about it. We'll say it's monotonic. But if one of these terms starts to go up again or increase, then it's not monotonic. Okay. All right, let's take a short 5-minute break. It's 8:49. So 8:55, we'll start 9.2. So the summation of a sub n will be equal to a1 plus a2 plus a3. So you're adding all the sequences, all the terms of the sequence. That's what a series is. All the way until a sub n and forever. So this is an infinite sequence. Series. Looks ugly. Okay, so S of n would be called the nth partial sum of a sequence. This is called the nth partial sum of a sequence. Okay, let me give you some definitions. Definition of convergence and divergence of a series. So for infinite series, the nth partial sum is called S sub n, which is equal to a1, a2, a3, all the way till an. Now, if the sequence of partial sums converges, then the series itself converges as well. Okay. Now, when we'll say S of n converges to S. So this is the series of partial sums. This is the limit, or the what it converges to. Okay. But if the sum diverges, then so does the series. So also, if S sub n diverges, then so does the series of A sub n. Okay. Now let me give you your first definition for one of the first ones. So theorem 9.6, convergence of a geometric series. So for chapter 9, you kind of have to try to point out or figure out what type of series we're dealing with and then use the appropriate technique. So this is the first technique, a geometric series. So a geometric series with ratio r diverges when the absolute value of r is greater than or equal to 1. If r, absolute value, is less than 1, then the series converges. This is what you're gonna have to check for. Converges to the sum. To the sum, this guy here. So n equals 0 to infinity of a times r to the n, which is equal to the sum of a over 1 minus r. But this only happens when r is less than or equal to 1. All right. So there's a bunch of theory here. So let's try to apply some of it. For me, it always makes more sense once we start doing things. Find the sum of the geometric series. Or, yeah, that's fine. So this is what the test questions will look like. I'm just going to give you a series and ask you to determine if it converges or diverges. And sometimes I'll ask for the sum. So the R is this piece right here. Sorry. Right, that's what the R is. Sometimes you can't see it. You have to figure it out yourself. But right here, it's given to you right away. So A is a number on the R. R is equal to 2/5. Since R is less than 1, that means it converges, right? That's what we said. So in English, since R is equal to 2/5, which is less than 1, then the geometric series converges. All right, so but they want to ask they didn't just ask for that, so they want to know what the heck the sum is. Okay. So the sum would be equal to this. So the sum because geometric will always end up this way thanks to the theorem. So it'll equal to 4, which is A, over 1 minus R, 2/5, which will be 4 over 1 minus 2/5, that's 3/5, right? Which becomes 20/3. So this is the sum that the series converge to. So you add this an infinite number of times, it eventually ends up as 20/3, which I think is kind of neat. All right. Any questions on the first example? All right. You also run into kind of like a telescoping type of series. I don't know if you'll see it on the homework or not, but just in case. So find the sum of this converging series, right? That's the question. So the sum as n equals, I don't know, 1, I guess, to n. One over n plus 1 minus 1 over n plus 2. So the sequence of partial sums, S of n, is what you do is you take all numbers up until n and you stop there. So it'll be 1/2 minus 1/3 plus 1/3 minus 1/4, right? That's what the sequence is telling you, plus 1/4 minus 1/5. So it'll keep doing that all the way until 1 over n plus 1 minus 1 over n plus 2. So basically, you'll see that the last and first, last and first, last and first, until I get to the last one. So I'll be left with only these terms after all the cancellation, right? Once you look at the pattern. Okay. So when you take the limit, remember we said that the limit of the partial sums as n approaches infinity, if that limit exists and converges, then so does this original series. So you take the limit of the partial sums, so as you can see, this limit goes to 0, so the limit is 1/2. So the limit, so since, let's put it in English, right? Since the limit of S sub n is equal to 1/2, then S sub n converges. Therefore, the series of 1 over n plus 1 minus 1 over n plus 2 also converges. Any questions on the example 3? All right. You may also have a sequence that requires partial fractions. So at this point, you guys should be comfortable with partial fractions, I hope. Find the sum of the convergent series. Okay. So notice how this can be factored, right? Into 5n plus 2 times 5n minus 3. Which means you could use the partial fractions and separate this as a over the first one. I'll come out of space there. As n approaches 1 to infinity of a over the first piece plus b over the second piece. So you'll have to do your partial fractions like usual. Okay. So start with both sides of the fraction. So 6 over the LCD here, 5n plus 2, 5n minus 3 equal to a over this plus b over this guy. Multiply everything through. That would give us 6. 6 equal to 5n times a. Oops, I guess now this pen's failing me. That's cool. Plus 5n plus 2 times b. This will give us, once you multiply everything through, just damn, man, this pens suck today. This would be 5. Nope. Still not working for me. Five a n minus 3a plus 5bn plus 2b. Create your system like usual. This will create a system of, let's see here, 5a. Five and 15. Actually, that's supposed to be 5. Maybe it's just this paper. There we go. Jeez. All right, so the parts with the ends would be equal to 0. The parts that are constant would be equal to 6. So solve this matrix, which will be on the calculator or by hand, whatever. I'm not going to waste time on this. This would be negative 6/5 and 6/5. So A is negative 6/5. B is 6/5. So now we have the series. It then goes to, then starts at 0, 1, I guess. Okay. So negative 6/5 plus 6/5 over 5n plus 2 and 5n minus 3. There we go. All right, so you take these limits, which will be, looks like, yeah, let's factor out those 6/5 first because that's confusing. So we'll pull out the negative 6/5, leaving me with 1 over 5n minus 3 minus 1 over 5n plus 2. So it'll be just like the other one, a telescoping series. So they're going to cancel out, right? Starting at 1 to infinity. So if I start expanding this, I'm going to put the 6/5 way out here. We're going to get, plug in the 1, that'd be 5 minus 3 is 2, so you have a half, minus a 7th, plus a 7th, minus a 12th, plus a 12th, minus a 17th, right, all the way till 1 over 5n minus 3 minus 1 over 5n plus 2. So everything will cancel, the first and last terms here all the way until here. So I'd get 6/5 times 1/2 minus 1 over 5n plus 2. So plug in all the numbers, add this stuff up. This would go to 0, right, when you take the limit. So it will be simply 6 over 10, which is 2/3. Oh, sorry, 2/5, 3/5. What am I talking about? All right, so this is actually S of n, by the way. Since S of n converges, then so does the series of A sub n. Just to save time, A sub n is this guy, right? Is there any questions on that? I mean, all we do is split up the series, did partial fractions, and then did the same thing we did in the last example. All right. Let's finish 9.2. There are 9.7 properties of infinite series. So similar to the ones for the sequences, but let's go ahead and write it all out. Let the series A sub n and series sum of B sub n be convergent, and let A, B, C be real numbers if the series A sub n is equal to A and the series B sub n is equal to B, then the following series converge. So number one, so the series of C times A sub n is equal to C times A. Number two, the series of n equal to 1 of A sub n plus or minus B sub n is equal to A plus or minus B. Okay. We give the most important theorem, I think, for series 9.8. The limit of the nth term of a convergent series Okay, so here's the idea here. So if the series n equal 1 to infinity of A sub n converges, then the limit of A sub n of the sequence must be 0. And this is the important part. It works in reverse. So theorem 9.9, we call it the nth term test for divergence. So if the limit as n goes to infinity of A sub n is not equal to 0, so basically what you do is you look at the sequence part and test, is it 0? If it's not, you're done and the series diverged. If it is 0, then we're going to go do different tests to find out what's going on. Then the series of A sub n diverges. So remember, it only tells you if it diverges. If it says If the limit is not 0, then the series diverges. That does not mean that if the limit is 0, it converges. Right? It says if it converges, then the limit is 0. But I cannot say that if this is 0, then it converges. It does not go that direction. The logic only goes this way. But the contrapositive, right, in logic, if it's not 0, then it's divergent. So that's something you could say. Okay, so that's the end of 9.2. It will be, so whenever we start a problem that asks for divergent or convergence, first thing you should do is check this. Check the limit of that sequence. Okay, let's take a short break. It's 9:28. Let's come back at 9:35. All right, so theorem 9.10. The integral test is similar to, very similar to what you did in 8.8 with the improper integrals. So it's basically the same thing. It's just that you're applying it to a sequence, and if it converges, then the series converges. If the integral converges, the series does. So if f is a positive continuous and decreasing for x greater than or equal to 1, and a sub n is equal to f of n, then this series can be changed into the integral n equals to 1 from 1 to infinity of f of x dx. So the integral test basically says that either both converge or diverge. All right, so let's go ahead and start with the examples here. And just to be honest, the integral test is usually your last resort because it requires you to do an integral, and the integrals may not be easy. So depending on the sequence given, do integral only if you can't figure out any other way to find out if it converges or diverges. Apply the integral test. To the series. All right, so first thing you should do when you do these types of problems is to take the limit of the sequence, right? So the limit of a sub n as n approaches infinity. So this is the nth term test right here. The limit of n over n squared plus 1 as n approaches infinity. This is equal to 0, right? The limit. So since this limit of that a sub n, the sequence part, is 0, then it doesn't tell me anything. Basically, this means that I need to use a different test. And the test I'm going to choose is the integral test, which they already told me, but that's the habit I want you to do every single time. You look at the question, take this portion here and take the limit and determine if that sequence is not 0. If it happened to be anything other than 0, I would just say diverges and I'm done. Move on to the next question. But sadly, that did not happen. So we will take the limit. This one goes to n of x over x squared plus 1 dx. So we're going to do the u substitution, right? There is no 2, so du over 2 will replace x dx. So this will be the limit as n approaches infinity of the integral 1 to n of du over 2 over u. So that limit will simply be now let's go ahead and replace the u again. So ln of x squared plus 1 from 1 to n. Now you can already tell, right? If I take the limit as this goes to n, this would be infinite. So this integral diverges. So since the integral diverges, then so does the series. Does that make sense? So just check the integral. If the integral doesn't converge, then right, well, let's do another one then. But remember, it has to be, I forgot to mention, well, I mentioned in the definition, but it has to be a positive function, continuous and decreasing. I didn't check on this guy because it's pretty obvious, right? This will always be positive. And since the bottom is bigger, it's going to keep decreasing as n gets bigger from 1 to infinity. So we were allowed to use the integral test because of that reason. Example 2. Apply the integral test. 2. This guy here. All right, so we should check two things. We should first check the limit of the sequence and check if it's 0. That way, if it isn't, then we can just be finished. So the limit of the sequence will be 0. Therefore, I got to do more work. Oh well. So what we're gonna do, the next thing we're gonna do is check, is this continuous after n greater than 1 or equal to, n greater than or equal to 1. So a sub 1 is equal to 1 over 2. A sub 2 is equal to 1 over, what is it? 5, right? Yeah. A sub 3 is equal to 1 over 10. And it's always going to be positive. It's always going to be decreasing. So since a sub 1 is less than a sub 2, which is less than a sub 3, right? And a sub n is always positive for n greater than or equal to 1, then we can use the integral test. I didn't mention that last time. So now you're going to take the integral as n goes to infinity of the integral from 1 to b of 1 over x squared plus 1 dx. So we should know that integral is pretty common, right? That's going to be the limit as, I should use b here. B goes to infinity of arc tangent of x from 1 to b. So that would give me arc, crap. That will give me the limit as b goes to infinity of arctan of b minus arctan of 1. So when arctan goes to infinity, that only happens as you approach the asymptotes. And that asymptote is going to happen at pi over 2, right? Because you're undefined at pi over 2 for tangent. Arctan of 1 gives me the angle of pi over 4. So the answer will be pi over 4. So since the integral converge to pi over 4, then the series is convergent. All right, guys. You guys have any questions on What is a sequence? What's the difference between a sequence or a series? How do you check if a sequence converges? Um, is that making sense?
Yeah, just need to practice. That's all.
We'll do one last thing and we'll call it a night because I know it's a lot of
Okay.
stuff.
Mm-hmm.
All right. So convergent P series. This is like the easiest test. All you gotta do is look at a number. This is kind of awesome. So suppose you have this example. Um, so the P series is n equals to 1 to infinity of 1 over n to the p. This is considered to be a P series type. So you have 1 over n and you have a p there. So this type of thing converges when p is greater than or equal to 2. So you got to check the number. Diverges when p is between 0 and 1. Okay. So for example, determine if the series converges or diverges. All right. So sometimes they'll just give you a pattern and you have to come up with the sequence or the series. So they might just give you this. Say, all right, does that converge or diverge? That's A, by the way. So you have to figure out the pattern. I see that it's going from 1, 2, 3, 4. So the series is starting at n equal to 1 to infinity of 1 over n, right? When n is 1, you get 1. When n is 2, you get a half, right? But now that I know what the sequence is, so since p is equal to 1, then the series diverges. That's all you got to do for these types. Okay, so those are the easier ones. We should technically check the limit, but since it's so obvious, you don't have to. All right, guys. Well, we'll stop here. If you have any questions, let me know. And if not, you can head out and have some math dreams.
Okay. All right. I guess I'll see you Thursday.
See you Thursday.